All right. And I'm going to start reviewing what we already saw, and then we go for the new material. So we started this chapter 4 talking about the time-dependent Schrödinger's equation. As we had already done, oops, someone else coming. As we had already done in chapter 2, we said, well, how are we going to solve this equation? Well, if the potential, now the potential will be something that it will be in 3 dimensions. So the potential may depend on X, Y, Z. But if it does not depend on time, we have an advantage. Okay, there are many people coming. Okay. Okay, so if the potential does not depend on time, we have an advantage. We said we can break this equation into 2. One equation is the one that depends, is the function that depends only on time. No, this phi here that depends only on time. And the other equation is the equation that we call the time-independent Schrödinger's equation. And this one, to solve, we need a potential. Okay, so the top one is the easy one to solve, is the one that gives us the time dependence, is the exponential in time. So our goal is to solve this equation here, the time-independent Schrödinger's equation. Okay. A participant has, okay, so this other equation here is the time-independent Schrödinger's equation. To solve it, we need to know what is that potential. All right. It's 3-dimensional, so we said that we can write that Schrödinger's equation like this, using the Laplacian, where this thing, that this symbol there is, the 3 derivatives in X, in Y, and in Z. All right. Now, to solve that equation, we need the potential, and we said, well, let's play with the potential that if I write it in spherical coordinates, it would depend on the distance, it would depend on 2 other angles. But if it does not depend on these 2 other angles, this is the kind of potential that we call central potential. Again, we have an advantage, and we can split that equation into 2. So if it does not depend on the angles, we are going to split that equation, the Schrödinger's equation, the time-independent Schrödinger's equation. We split it into 2 pieces. One that only depends, that will give us the function that only depends on the distance r, and the other one that will give us the solution that depends on theta and phi. We already solved this part. This is the one that we call called spherical harmonics. We said that this spherical harmonics depends on L and M, when L and M are integers. And I'm going to write oops, no, there is nobody else. Okay. And the solution for this one we already talked about, normalized, and this I'm going to copy from your book, is equation 4.32, if anyone is following the book. So is that 2L plus 1, and then L minus M factorial. All this is in the square root 4 pi, and then L plus M factorial. More people coming. All right. Okay. And then what else? Then there is the part that depends on the angle phi, which is the one that comes with that M, the integer value. And there is this PLM, cosine of theta. This is the, what we said, associated Legendre's function. And there was an equation to solve, to find these ones. What else did we say about this one? That M, that integer M, since to obtain this equation, or since to obtain this function here, there are some derivatives, and look back in the book, this M could not be any integer. It was limited by the value of L, which means, because if we go beyond that, then the derivatives would just give us 0. No? So which means that this M would be minus L plus 1, all the negative integers, minus 1, then 0, and then the positive is 1, 2, 3, and then L minus 1 and L, which means there are 2L plus 1 possible values of F. Okay, we already went through this. Now what is remaining to do was to solve this one, the part that depends only on R. Then what we did here, try to get another page. What we did here was to try to simplify the equation that depends only on R, to put it in a form that was kind of familiar to us. And so we wrote that R as a new function, U of R divided by R. And when we did that, then we found an equation that looked more familiar to us, the equation for the U function. And what was that? Minus h squared over 2m, second derivative of U. So this reminds us of the kinetic energy of the old Schrödinger's equation that we had. Then comes the potential. So here we have the V, the potential, but also some extra terms here. This h bar, 2m, L plus 1 over R. This whole thing here, oops, R squared. So this whole thing here is what we called an effective potential equals to energy U. So this looks very similar to our old time-independent Schrödinger's equation. We even said that the normalization for that U function looks very similar to what we used to do. What do I mean, what we used to do? Because the normalization for the R function has the R squared, the little R squared dr, because we are using spherical coordinates. Okay? All right. Then we were trying to solve this equation here. Now, to solve this equation, we really need the potential now. And we said, well, oops, someone else is coming, Nick. right on time. So we said, we need a potential. Let's try to solve for one potential that is not too complicated and which we can solve exactly, which is the one for the hydrogen atom. So what is the hydrogen atom? We have just the nucleus is just a proton, and around we have just one electron. So it's the easiest kind of atom that we can have. And now is the potential. This V, now I told you the book uses V, but often somewhere else is coming, William. But often in your books, we used to call this U. No, in many books, it calls it U. This V is the potential energy. Anyway, so the potential energy for this hydrogen atom is, we have just proton and electron, so E squared, the charge is the same for the two. There is a constant here, and it depends on the distance between the two. So this is what we are going to put here in our potential energy, and we will try to solve. In this process, what we did was to introduce some constants, just because it became easier than carrying all of these 4 pi L's around, H bars around. So we try to simplify all these symbols. And then what is the equation that we wrote? Now, what are the symbols that we wrote? A kappa, which we define as being minus 2m, the energy, over h. Why minus there? Because, so why minus here? Because we are thinking about energies that are negative. When we are talking about this potential, now or the effective potential, if we would sketch that effective potential, we said that, let me go back, when R is very small, this is the term that dominates, and this term is positive, so our potential starts up here. But when R, this is a function of R, when R starts getting large, this part here is the one that will dominate, so there is a crossing point and we become negative. And then when this R is very large, we go something like this. So we said that different kinds of states, oops, and it is coming. Okay, so there are different kinds of states that we can solve. Well, different ways to solve Schrödinger's equation. The energy could be positive, and then we have scattering kind of states. or the energy could be negative, and we have bound states. We are studying just the bound states. Now, when the electron is really attached to the proton, forming that atom. Okay, so this was the first symbol that we created to simplify the equations. And what are the others? Then there was that rho. And so instead of using our variable r, we started using variable rho, which was defined again as kappa r. Okay, so this is our new variable. And we also defined a new combination of symbols, which is this rho zero. This rho zero is very important because that's the one that is going to give us energy at the end. No? That's how we ended the last class. So what is this rho zero? We combine all of these symbols that we have around, and we wrote it like this. Mass, this M is the mass of the electron. That was a question that Thomas had asked, because you see that there is, when we are solving this equation, there is the M here, this integer. These are the ones showing up in the equation itself. Is not the integer, is the mass of the electron. In your book, they even put a little index E here to remind you that we are talking about the mass of the electron. Okay, I'm not carrying this little E because it makes it cumbersome, there are too many symbols. Okay, but this is the mass of the electron, the charge of the electron square, and then 2 pi epsilon 0 h bar square, and the important thing, kappa. Okay, because why I'm saying it's important, because kappa has energy. No? Kappa is the constant associated with energy. Anyway, we did all that to simplify the equation. I'm going to write the equation that we wrote, the equation for the u. So the u function became written like this. And on the right side, we have number one, those two symbols that we introduced, rho zero and rho, and then L plus 1, that integer from the spherical harmonics that we already had, and equal to E. And then we stare at this equation, just as the people who are trying to stare at this equation. How are we going to solve? Okay, so how are we going to solve this equation? We said, well, let's try to look at some extreme cases. Let's try to start by looking at when rho is very large. When rho is very large, the largest term in this right side is number 1. So the equation became very simple. This became our equation, and we know how to solve. We said, oh, then this u is going to be the exponential minus rho, or positive rho. And then I said, no, but this one I don't want, because if rho is very large, this is going to explode. So this is the only one that remains. Then we looked at rho very small, and we said, well, the solution now for this equation will be an equation that this term now is the largest one, because rho is very small. So now our equation became this. L plus 1 over rho square u. And this one we solved. We said, well, this is a polynomial, and we can write this u now as C rho L plus 1 plus D rho minus L. If you put this back into equation, you'll see that it solves. Someone else is coming. Okay. All right, so then we said, okay, but now when rho is very small, this one is not good because this is going to explode, so we keep only the other one. So the solution for the u was the rho L plus 1. So this piece here. Then this part here. So E2 minus rho. And now how are we going to stitch all that? We are going to put another function of rho here, and our goal now is to find this guy. Okay, so we said, I think this should be our solution, because this will take care of the solution when rho is very small. This will take care of the solution when rho is very large. And in between, there is something that I have to find out what it is. Okay, so we pick this function, put it back into this equation here. And then we came up with an equation for this rho. So this V of rho. Okay. this is, if anyone is looking at the book, this equation here is 4.60. The derivatives are just below. Try to do them, okay? Because then it's just a matter of doing derivatives and combining the terms. If you do them, we are going to arrive at the equation 4.61 in the book. What is that? The equation for V. So I'm going to just write this equation, rho d squared, the second derivative for V, and then 2, we have L plus 1 minus rho, whole bunch of things. First derivative, and then the part, the rho 0, the rho naught, 2, L plus 1, and then V equal to 0. So this is what survived and what we need to solve. And said, well, how are we going to solve that? We are going to try to write the V as a series, as a sum. As a sum, so of rho to some power. So this power is this j that is going from 0 to infinity. And we have to find what are these constants in front. Okay, as we said, a series can represent exponential, cosine, sines. No, there are many functions that can be represented as a series like that. So I'm going to write it like this and put it back into this equation. We did that. And then we are going to, by doing this, we find an equation for those constants, which are the unknown in this story now. Okay, I'm going to write the solution, then we'll discuss it. Okay, so we found, by doing that, we found an equation for these C's, for these constants there, which is written like this. Let me write and then we'll talk. Okay, in the numerator, we had 2, and then comes the j, which is the element here in the sum. Then we have L plus 1 minus rho 0 in the denominator, j plus 1, j plus 2, L plus 2. And all this multiplied by Cj. So that's where we arrived. And what does this mean? This means that if I have C0, so if I have C0, I can find C1. If I have C1, I can find C2. If I have C2, I can find C3, and so on. So this is the recursion formula. If I have 1, I can find all the others. So if I have 1, I can find the function that we are after. Yeah? So if I have 1, and how is this 1 going to be found? By normalization. So that's perfect. It looks like we solved our time independent Schrödinger equation, the radial part. So that's what we were trying to do. We were trying to find this r. We wrote it as a function of u over r. We found from this u, we rewrote things in terms of rho. So we found this piece, and now we finally seem to have found this v. Okay. Rho there is kappa r. So it's a function of r as well. So everything looks good, but then I said, oh, if we start studying this recursion formula, but for very large values of j's, we finally found out that this v would be an exponential. Let me see if I find the equation where this was given. Okay, so it's between 464 and 465 if anyone is looking, but we found that this would be an exponential. And then we said, oh, then we're in trouble. Because if this is an exponential, if I put it here, well, what is going to survive for this r, this function? Well, there will be now exponential of positive rho. And this is trouble because it's going to explode when rho becomes large. So it's, this cannot be. So something is wrong with our way to start this infinite sum, this series, we said the only way for things to survive is if we truncate this sum. Okay, so we have to do something, we have to truncate this sum, we cannot go all the way to infinity. All right, so then we said to truncate that sum, this sum is going to go from 0, so our v here, the sum will go from 0 up to some point. Not forever, it will be truncated at a certain value. We are writing this big N. What is this big N? What does it mean? No, so again, if I have C0, I find C1. If I have C1, I find C2, and so on. But I will reach a point where I will have Cn minus 1, and I'll say, okay, with that, I should be able to find Cn, but we'll say Cn does not exist. Cn is 0, I truncated. From there on, the series is dead, which means I will be from C0, C1, C2, all the way to Cn minus 1 only, and not beyond. So to guarantee that this will be 0, that beyond Cn minus 1, nothing exists, I come back to our recursion formula and put here. So we are saying that n minus 1 exists, j n minus 1 exists. Now this one, which will be n, will not exist anymore. So Cn will have to be 0. Okay, so I come to this equation and write what I just said. So let's do that. We are saying that, maybe I will write this equation again so you understand what I'm doing. So Cj plus 1 equals to 2j plus L plus 1 minus rho 0, j plus 1, and then j plus 2L plus 2. So what we said is, I'm going to put here in the j n minus 1. Okay, so this means that this part now becomes 2, whatever is j is n minus 1. Okay, so this is our numerator, and the denominator, whatever is j, I'm going to put n minus 1. So n minus 1, oops. N minus 1. Okay. So this is our Cn minus 1, and we are trying to find the Cn. But we said Cn has to be 0, okay? Which means the numerator here has to be 0. So we found our equation to truncate. Oh, some people are coming. Oh, wait. Who are they? Carlos and Danya. Okay. Neat. All right. All right. So continue. So this numerator has to be 0. And so we found an equation which is 2n plus L minus rho 0 has to be 0. That's how we truncate. That's how we guarantee that this series now is not going to give us an exponential. That series is just giving, so this series here is just giving us a polynomial. So now we have a solution that does not explode. It's physically, it's very good. This is the important part from now on. Okay, so for those who are arrived a little late in the class, you didn't miss that much. It was a review. So what do we go from now? Well, first thing that we did here was we defined a new entity, a new symbol here for this big N plus L. We said that big N plus L, I'm going to call it little n. Okay. So we arrived at this important equation, which is rho 0 is equal to 2 little n. And why is this very important? Because of what I said in the beginning of the class. Remember what rho 0 is? Rho 0 is related to kappa, rho 0 is related to energy. So let's write what this rho 0 is again. Rho 0, let's put it here. Rho 0 is we have the mass of the electron, the charge of the electron square, some constants, 2 pi epsilon 0 h bar square, and the important thing, kappa. Yeah, and what is kappa? I'm going to put kappa square here. Kappa square is minus 2m energy divided by h bar square. So if we combine all this, we are now going to be able to find an equation for the energy. Okay, so let's do this together. What I'm going to do is I'm going to start with the equation for rho 0, but I'm going to put everything squared. Okay, so rho 0 squared is mass square, charge now to the fourth, 2 pi epsilon 0 squared, h bar to the fourth. Now, kappa here, I'm going to use this equation here. So kappa is minus kappa squared, no? Minus 2m e over h bar. Okay, so this is kappa squared. And all this is equal to what we found here, but I'm using squared everywhere. So this is equal to 4n squared. All right. So this is an equation for you to play with. Rearrange things so then you can finally find an equation for the energy. And it's an equation for the energy which I'm going to put with the index little n, because we see that it depends on n. So I'm putting here this index little n, and this is equal to, there is a minus sign because of this minus sign here. So there is a minus sign there, and then comes a whole bunch of constants. So let's go. Mass of the electron, 2h bar square, e charge square, 4 pi epsilon 0, all this squared, 1 over n squared. Okay, so all this is a whole bunch of constants. And what, how does this energy change? With this 1 over n squared, right? So we can also write this as E1 over n squared, where n is 1, is 2, is 3, and so on. So E1 is, so let's write here, E1 is the energy for the ground state. E1 is the energy for the ground state, is minus mass over 2h squared, e squared, 4 pi epsilon 0 squared. And if you put all these numbers there, because you have mass of the electron, charge of the electron, and so on, you're going to get minus 13.6 eV. Yeah? This is the amount of energy that we need to give to this atom to remove the electron, to ionize this atom. So this is the binding energy. Well, it's the ground state energy. And it's the amount of energy that we have to do to remove this electron from the atom. Okay. You see that n starts in 1, so the ground state is 1. We cannot use 0 here. 0 we only use for the harmonic oscillator. We cannot use 0 here because it wouldn't make sense. Okay. Okay, now that's where we finished the class last time, and now we want to talk a little bit about this equation in terms of what Bohr did. Now, what we said is, this is what we derived after some effort here, but we are able to derive, even in an introductory course on quantum mechanics, so it's great. But using Schrödinger's equation. But Schrödinger's equation came in 1926, while Bohr was trying to find this equation in 1913. So what is it that he did? So what I'm going to do now is a review of something that you may have seen in a course of modern physics, which is not in your book, but I think it's important, okay, to explain how did Bohr reach this equation. Okay, so no Schrödinger's equation, no idea about wave functions. It's like the beginning of quantum mechanics, so he's going to resource to what it was known to them at the time. But before I tell you what Bohr really did, let me give you some motivation. What is it that people are trying to do in the end of the 1800s, no, 1890 more or less? What is it that they saw? Well, suppose I have here a recipient with some gas of some atomic gas. No? So for example, it could be a gas of hydrogen. And I excite these atoms, inject some energy, excite these atoms. So what will happen is these atoms, now you know, you have even the language to say these atoms will de-excite and they will emit some light, okay? If I pass this light through a prism, what is going to happen is we are going to, you may have seen, I'm playing with a prism, we get like a rainbow. No? We have lines of different wavelengths, of different frequencies. Yeah? Okay, what are these lines? No, these lines of different frequencies. Frequencies is energy. No? So these lines here correspond to the spectrum of that atom. So each color that we have here, red, blue, and so on, is a different frequency. Different frequency, different wavelength means different energy. So these lines form the spectrum of this atom. And what is beautiful, especially for Sangeeta, John, the people who are doing astrophysics, you must have learned about this. Each atom has its specific spectrum. So the spectrum is like the fingerprint of the atom. Just by looking at the lines, we know, okay, these are the lines from hydrogen. Oh, these are the lines for lithium. And this is the way that we know what the stars are made of. Now, how do we know that a star is made of helium or hydrogen? We don't go there. We don't get samples from the stars. We get just the light. No? When I use the word light, I'm talking about electromagnetic waves. No? So it could be infrared, it could be ultraviolet, it could be visible. No? So, and that's what we get from the stars. So we pass it through the prism, we see these lines and we say, oh, this is a beautiful little new star made of hydrogen. It's a newborn. We look at another one. Oh, this is a star mostly made of helium. So it's already a teenager. It's already burned some of its hydrogen and it's now has lots of helium. So this is how we know about the stars. Anyway, so this spectrum. So people were seeing that and they were playing with different kinds of atoms, different kinds of gases, and they had this and they had no idea of what was coming, where it came from. They have no idea about the structure of the atom yet. And they started coming up with some equations for these lines. One of the equations for the hydrogen is the equation that, I'm going to write the equation, is something for the wavelength where there was a constant. This is called Rydberg constant. It's like Rydberg put things together. And 1/2 square minus 1/n square. So you see the n square showing up, the n square that we talked about from the equation of energy. See, 1/wavelength. Wavelength is connected with frequency. This is speed of light, wavelength, frequency. Frequency is related to energy. So you see that this equation is connected to what we saw, the 1/n square. And what is this constant? Well, from many lines that they were studying, they came up with an equation for this, with a number for this constant, which is 1.1096775.6, 1.2, 1/meters. All right, so that's what Bohr has, and that's what Bohr is trying to make sense of. He didn't have the tools, so he came up with some postulates. So what are the postulates? Which, as I told you last class, is wrong, but help him to get the right answer, not the sleepwalkers that I was telling you about. So what is it that he said? First postulate. He said, well, the electron must be moving around the proton in a circular orbit. This makes no sense. As we said, the electron is everywhere, it's a wave function. Well, he said it's moving in a circular orbit, thinking about planetary system. And why? Well, because there is Coulomb attraction. There is this electric force. Why the electron does not collapse inside the nucleus? Because it has a velocity, just as in the planetary system. Okay, and it's all classical. So following the laws of classical mechanics. Now, second postulate. There are some orbits, but not any possible value of orbit. There are some constraints. So there are some orbits, but only those for which the angular momentum is discrete, is n of h bar. This is the n that is showing up in these equations, okay? So, but he has no idea why he's putting these things. No, it's the beginning of quantum mechanics. Planck was talking about energy being discrete, and this h bar is showing up around these equations. What else? Well, the electron is moving. There is a force there, the electric force. So this electron is accelerated. We know that charge is accelerated, they should emit light, no energy. How come this electron is not emitting anything? Again, postulating, he said, if the electron is in one of those allowed orbits, it doesn't emit. It doesn't radiate. Why? I don't know. I'm putting this as a postulate. That's his point. No? Now, if this electron moves from one allowed orbit to another allowed orbit, it cannot move anywhere else. So if it moves from one allowed orbit to another one, then it will emit. Then there'll be radiation. And what kind of radiation? The frequency that this electron will emit will be determined by the difference of those energies. Okay, so the energy of this radiation, which is the photon. Huh? So the energy of this radiation is the difference between the energy that it had here and the energy that will have at the end. Okay, so I can say that this frequency is initial energy minus final divided by h, not h bar, h here is Planck's constant. No? H bar is Planck's constant divided by 2 pi. Okay, you're super quiet. You feel free, you can interrupt me, okay? All right, so what are we going to do with this? These are the postulates, and how did Bohr proceed with this? He said, okay, so my electron is moving due to electric force. Using classical mechanics, force is equal to ma. So this force here is 1/4 pi epsilon 0. This is just a constant. Then we have the charges of the two entities here, which is proton and electron, same charge, divided by distance between them, r squared. So this is the force. Now, what we have here is centripetal acceleration because we have this circular motion. So mv squared over r. Purely classical mechanics. Okay, what are we going to do with this? We are going to extract an equation for the radius. Okay, so if you simplify things, you can write that the radius is equal to, let me see, r goes up, so we'll have 1, 4, 5. So tell me if you don't find it. So the only thing that we have is this r. All these survive. I'm putting this r up. And what is on the right side, I'm putting down here mv squared. So I found an equation for the radius. But what I'm going to do next is, remember the other postulate, he said that the angular momentum had to be NH bar. What is angular momentum? Angular momentum is momentum, linear momentum with R. No? So linear momentum is mv, R equals to NH bar. So from here, I'm going to find an equation for the V. No? So the V is NH bar over MR, and I'm going to put this here. And now we rearrange everything, and we are going to finally end up with an equation for R. Just by playing with these simple equations that you know from introductory courses in physics. So to put the V here, we'll have to square things, which means this N here will be squared. So let me write what we get. We have H bar square over, now let me see. Yeah, I think I didn't want to waste time doing this, but I think we'll have, okay, so an N H bar, K here is 4 pi epsilon 0 square. Okay, let me do this, otherwise I'm going to make a mistake. Doesn't hurt to do this. Yeah? Okay, so we have R is that constant. We have E square, M, and now we have N square, H bar square, M square, R square. So this M cancel, and now we have an equation for R. So we see that there is an R here and another one. So the equation for this R is now 4 pi epsilon 0. So this came up. And then we have at the bottom E square, M, and H bar squared. Okay. And N square. I think this is now right. Okay, so we found an equation for the R. This whole thing that is here is what we call Bohr's constant, Bohr radius. If you put the numbers for these symbols, this Bohr radius is, this is something you may have learned before, no? For 0.5 angstrom. This is the radius for the ground state. No? So Bohr radius is the radius for the ground state. We found that. You see the N square showing up there, so which means larger N, N larger than 1, the radius is larger. So the further away this electron, well, the more excited this electron is, the further away it is from the proton, the higher probability to find it further away from the nucleus. Okay, what else are we going to do? Let's now think about the energy of this electron. So the energy of this electron has the potential energy and the kinetic energy. So the kinetic energy is 1/2 of mv squared, and the potential energy is what we wrote in the beginning when we were talking about solving the hydrogen atom. So it's minus the constant E squared over R. Okay. All right. Using what we just found for the V above, so let me use this equation. So using what we are doing for the V above, we can rewrite the energy as minus 1/2. I'm going to tell you how I came to this, okay? How did I come to this point? Well, I substitute this part, the kinetic energy, using what I know for this electron moving around the nucleus. Now we said that the electron is moving due to the electric force. So the electric force is this. So here, what I did is I multiply both sides by half. I cancel this R. So this is the kinetic energy, which is this part, which is very similar to this one. There is just an extra half in this story, and this is positive. Okay? So if you put this term here, you find what I wrote. Okay? You're not asking, so I'm assuming that it's all clear. Okay, so we found this equation for the energy, but we also have an equation for R. So if I pick this R, this equation for R, and put it here in this equation for the energy, we are going to find exactly what we had before. We are going to find, so let me copy this again. We are going to find the energy that we wrote before. Four pi epsilon 0 squared 1 over n squared. This is what we had obtained using Schrödinger's equation. That's also what Bohr was able to obtain using just classical mechanics. So he is lucky. He was very lucky. No, this is a simple. The atom is so simple that it worked well. If you try to use this reasoning that Bohr used to more complicated atoms, even for helium, from helium on, you cannot. No, it's not going to work. Things will break down. You will really need to go into Schrödinger's equation. No? But he was very lucky. As I said, the sleepwalkers. No? You arrive at the right answer, taking wrong path. Okay. So I hope you will remember these things about Bohr and study if you haven't seen this before, and ask me questions. Okay, so this is, even though it's not written in your book, this is part of our classes. Okay, so the postulates, understanding, knowing about the postulates and playing with classical mechanics to be able to find that energy. Okay, so it's something that I expect you to know as well. Okay, so what are we going to do with this next? Well, coming back to those symbols that we have introduced, that kappa that we have introduced, now that we have the energy, we can also write this kappa as 1 over AN, where A is that Bohr radius that we talked about. It's a combination of symbols, 4 pi epsilon 0 h bar square mass of the electron E square. Okay, so this is Bohr radius that we found above. That kappa that we have used before, we can write in terms of A. Remember the rho. We wrote the solution in terms of this rho, which is kappa R. So this rho, now that we have Bohr radius, we can write this rho as R, the real variable, divided by Bohr radius n. So this is going to be useful for what we are going to be doing now. What is it that we are going to be doing now is, okay, now that we have everything, let's finally write our solution. The wave function for the time-independent Schrödinger equation in 3 dimensions for the central potential. So what is this wave function? It depends on R, theta, and phi. What is R? R is that function of R, which I'm going to put indices here. R depends on N and L. Okay, there are 2 indices. Then there is the part that depends only on angles, which depends on the L and M, theta and phi. So the wave function depends on N, L, and M. So 3 different indices. Where are they coming from? This part we already know. This is the new one. Why does it depend on L, N, and L? Because this solution is written as rho L plus 1 exponential minus rho, the V of rho divided by R. We just said rho depends on N. You see this equation here. right? Rho depends on n, so this solution depends on n. And you see an L here, so that's enough to tell us our solution depends on two indices, n and L. What is n and L? So now it's names, okay? But n is what we call the principal quantum number. Principal quantum number. These are names, but it's important to know that they exist. What are they about? Well, they give us the energy. The energy starting from 1 and above. Okay. Then there is the L. L is another quantum number. The name is azimuthal quantum number. And the M is another quantum number. We call it the magnetic quantum number. So these are names, but you will see in the next class that these things, L and M, are related to the angular momentum. So the electron is moving. So we have this proton, we have this electron around, but it's not an orbit as what we're saying is a cloud around. So we have this wave function spread out, and this wave function will give us the probability to find it here and there. Maybe if I have time, I'll show to you some drawings, some pictures of these wave functions. Okay. But so here I am. We want to find, we want to write down now these solutions. We are going to start by thinking about the ground state. So what is the ground state? The ground state is, well, as we said, when n is equal to 1. Okay? So if I want to write that wave function for n being equal to 1, I have to decide what is L and M going to be. Well, how I'm going to decide about L? We're going to decide about L thinking about that part of the solution, the V. Remember, the V goes from j equal to 0 up to n minus 1. We said that is truncated, so that's the series. Here we have some constants, and we have the equations to find these constants and rho to j. Okay, so this truncation will tell us how we are going to find that little L. Remember, the definition is that little n is big N plus L. This is how we define, which means that big N is equal to little n minus L. So if I rewrite our function rho, I have a sum that goes J0 up to n, little n, minus L minus 1. Okay. So this is the important thing. By looking at this, we'll know what is the value of L. Okay, so let's pick the example. If n is 1, the largest part of this series will be n minus L minus 1, which is equal to 1 minus L minus 1. So this is 0 minus L. Okay, so you see that L cannot be larger than 0. It doesn't make sense. Any other value for L would give us beyond what the series can go. Okay, so if n is 1, L has to be 0. Okay, so we are trying to find the ground state, so L here has to be 0. There is no other for it, no other possibility for it. Then how about M? Well, we said that M has to be, maximum value for M is L. So M also has to be 0. This is for the ground state. This is the wave function. So these are the indices, N, L, and M for the ground state. Okay. So coming back again. For the ground state, the wave function, the solution for the time-independent Schrödinger equation is 1, 0, 0, the indices, R, theta, and phi. Okay, so now let's try to fill all these parts. R, N, and L is 1 and 0. That's what we need. The spherical harmonics is L. L here is 0, so I'm going to put 0 here. M up here is also 0, theta, and phi. If you have started solving any of those problems for the spherical harmonics, probably you haven't, but today I'm going to list the problems that you should start solving. You will know that for L0 and M0, this solution is very simple. It's just 1 over 4 pi. Okay, so this part is solved. The part of the spherical harmonic is solved. It's something that if you haven't done, you will be doing from now on. Okay, so what remains to find is the part that depends on the radius, not the radial part. Okay, so let's write our solution. Well, we have the 1 over 4 pi coming from the spherical harmonics, and now we need the R. What is this R? Rho, L plus 1. But L is 0, so L plus 1 is 0. Then we have exponential of minus rho. Then we have the V of rho. This numerator is the U function. Remember that the R is divided by R. Okay. Remember what we wrote above, that rho is kappa R. So it's R over A N. But here we are thinking about ground state. So that means that our rho is R over A. And this is what we are going to be putting in the equation. So the solution, the radial part, I'm going to put this rho is R over A. This is what I wrote here. Exponential, this part here, exponential minus R over A. There is this R here, and there is the V, which we'll have to find. Now, how are we going to find the V? Is that sum J from 0 to, we wrote the top here is N minus L minus 1. N is 1, so this cancel. L is 0, so you see that our sum is just one element. Our sum is just C0 because it's the only thing that exists when N is 1. Okay, so this is just C0. Okay, so let's go. R10, the radial part for the ground state, is exponential minus R over A C0. So excellent, we're almost there. But we don't have the C0. So what is it that we are going to do? If I was in class, I would stop here and ask you. If anyone wants to scream there. You see? To find C0, nobody wants to say. Okay. So to find C0, what we have to do is normalization, right? Okay, so what are we going to do? Normalization using spherical harmonics means R squared dr. This has to be equal to 1. Okay, so let's put all this into this integral. The exponential square becomes 2. A square and the C0 square, R square dr equals to 1. This is what we have to solve. to find C0. I'm going to put the answer and then I'll come back to solve this with you. Okay, so the answer for the C0, if you solve this equation, is going to be 2 over square root of A. So let me put all this in our final solution. Let me write down what we have. We have the wave function for the ground state is then equal to the wave function, n is 1, L is 0, M is 0, R theta phi. We found that the radial part has this constant here, so I'm going to copy it here. Okay, so this constant. We also have this whole part here, so I'm going to copy that. Okay, over A. So this is the radial part. And then we have the part that comes from the spherical harmonics, 0 and 0 for the ground state, which is this. Okay, so the solution you put all these together, this square root of 4 with 2 cancel. We have exponential minus r over a pi a cubed. This is finally the solution. So that's what we are trying to do, right? Solving time-independent Schrödinger's equation. We found the energies, and now we found one of the wave functions, the one for the ground state. That's what it is. Yeah. We are going to find some others now, and there'll be others for you to solve as assignment. Well, it's not assignment as homework, not for grading, but important to learn. Yeah? Okay, so what remains for me to show to you is where this C0, how did we get this C0? We get this C0 solving this equation here, now this integral here. And how is it that we solve this integral is by parts. So I'm going to sketch this with you. Let me see if I'll just copy this below. We have here C0 square, A square, and now the integral. Okay, so this is the integral that we have to solve to find the normalization constant here. And how is it that we solve this integral? By parts. Yeah? So I can put this r squared here in the exponential and solve it by parts. So you can go on saying that this is, you can say that u is r squared and the dv is that. Okay, so then I let you to solve this, doing by parts. You have to do it twice, by parts twice, and then we'll find this constant. And that's it. Okay, so that's how we solved one wave function. But let's try some others. So this is the wave function for the ground state. How about for N2? N2, now comes the story, because if we are going to find the wave function, well, we have to determine again what is going to be L. And once we know L, what is going to be M. Remember what I was saying, how do we find L? We come here in the truncated sum for the V that goes from J0 to little n minus L minus 1. And we have to determine now what this L will be. N, in our case, is 2. No? We are thinking about the first excited state. Okay, so that means that our sum here goes from J0 up to 2 minus 1 is 1. no? And 2 minus 1 is 1 minus L. So now we have to think, what is going to be the possible values for L? Well, it's okay, L can be 0. L can also be 1. And this sum makes sense. So there are 2 possible values now for L. Okay? Which means, what are the possible states? What are the possible solutions for the excited state? 2, we can have L0. And if L is 0, M has to be 0. So this is one possible solution. But there are others. What are the others? Well, N2, L could also be 1. This also makes sense. That also allows us to make sense of that series. So L can be 1. And then what is going to be M? Well, M can be 0. This is a solution, but M can also be minus 1. That's another possible solution. And M can also be 1. Okay, so that means we have 1, 2, 3, 4 possible states, all with the same energy, E2. Okay, so there are 4 states with the same energy, so we have 4 degenerate states. This state is a possible solution. This is another possible solution. This is another possible solution. This is another possible solution. So there are 4 states that have the same energy, E2. Okay. So the first excited state has these 4 possibilities. Okay, so let me, we are going to try to find these solutions, okay? But let me try to explain the L with respect to the N. So what we are finding is, remember this, the series, no? That it goes from J0 to N minus L minus 1. So this thing here can be from how we decide this value here. Well, it can be 0, it can be 1, it can be 2, it can be 3, no, it cannot be negative. So it can be 0, can be 1, can be 2, and so on. So starting from 0. So how do we find the value of L? The value of L can be 0. No? If I put it here, then I have N minus 1. It can be 1, so then it would be value of N. And then it can be N plus 1 and so on. So the value that L can have, L can be 0, can be 1, can be 2, can be up to N minus 1. These are the possible values of L. Let's put this in this equation. If I write if I write L as N minus 1, this is 0. Okay, so this is the maximum possible value of L is N minus 1. So remember when we are talking about the ground state, N was 1, well, L could only be 0. Now that we are talking about N2, then L can be 0, L can be 1. It makes sense in our sum there. If N was, so let me write here. If N is 1, L can only be 0. If N is 2, which is the one we are trying to solve now, L can be 0, can be 1, and that's it. If N is 3, then L can be 0, can be 1, can be 2, and that's it. No? Because if we go back to this sum, if N is 3, no? So N minus L minus 1. If N is 3 minus L minus 1 means 2 minus L. So the maximum value that L can have is 2. Yeah. Okay, so you see that for each value of N, we may have many values of L's. And for each value of L, we have many values of M. And they form a group of degenerate states. Okay, there are 3 more minutes, so let me just tell you about this group of degenerate states. If N is 1, L can only be 0 and M can only be 0. So there is only one state with the energy of the ground state. If N is 2, well, now L can be 0, but L can also be 1. If L is 0, M can only be 0. But if L is 1, M can be -1, 0, and 1. So we have 4 degenerate states with energy E2. Pick another case, N3. L can be 0, and then M is equal to 0. L can be 1, and then we have -1, 0, and 1. But L can also be 2. That's the maximum value of L when N is 3. And then what we have? -2, -1, 0, 1, and 2. So that means 5 possibilities here, plus 3, plus 1. So we have 9 degenerate states. All of them with energy E3, and so on, okay? I'm going to stop here. I already talked a lot. It's almost 45. We are going to find the states 4 and 2 next class. And I'm going to start talking about also angular momentum, okay? And I'll come back to the story of the degenerate states. So I don't know if you're still there. I'm going to stop recording. How can I stop recording?